So we just finished talking about scalar line integrals, and now we're going to talk about our second topic, vector line integrals. Vector line integrals are really similar, and they have some uniquenesses. Like scalar line integrals, we need to have a function and a path. The only difference is, for our scalar line integrals, our function was a real valued function that our outputs were x's and y's, whereas in this case, our outputs are going to be vectors. This is a vector field. So our vector field, I represented my generic vector field here with all of these arrows. This is my vector field f of x, y. And I'm still going to have a path. When I input a time t, I should get out some point in space. But unlike our scalar vector fields where you could visualize the path in the xy plane and then the integral was representing the height along that path, giving you the area of that sheet that gets traced out. In this case, we have a different interpretation. That my interpretation is going to be, as I travel along some path, let's say this blue path is my blue path c1 of t, I'm asking myself, how much force does my vector field f of xy exert on my path c of t in the direction of c? So maybe these words don't quite make sense, but I'll describe them in a little more detail. So let's say that I have a particle that starts here at t0 and it moves to here at t5. As I move along this path, I notice that my vector field is exactly perpendicular to my path. So it is pushing on me, but it's never pushing in the same direction as I'm traveling. It's always pushing perpendicularly. So this would be an example where my vector line integral, and usually we write my vector line integral is going to be on my path c of my f, and we write dot ds to signify the fact that it's a vector line integral is 0 for my blue value, because this vector field is never helping me, it's never pushing me in the direction that I want to go. Whereas, let's say that I had a path that started down here and went up this way. This is my red path going in the positive direction. We see that for my red path, it's going to be greater than 0. I'm not going to compute exactly what it is, but really at each point along here, the vectors are helping me, and they're pushing me in exactly the same direction that I'm traveling. Conversely, maybe I'll write this as my green path. Let's say my green path started up here and went downwards, my green path. We see that I'm constantly working against my vector field. And so if I'm working against my vector field, it means that the amount of force that's being exerted, or the amount of work that's being done as I travel along this path by the vector field, is going to be less than 0. How much, and when I say force, really what I should say cumulative force. How much cumulative force does this vector field exert on c of t in the direction of c of t? And what's our other word for cumulative force? How much force that's being done as I travel along some certain period of time? One way that physicists call that is work. How much work is being done by my vector field as I travel along my path? So you can get an idea from some of these. I wish I had one more colored marker. I'll repeat red. I'll erase this red and erase it from here so as not to be confusing. But here's a new red path. Let's say that our red path, instead of going in straight lines, is now traveling at an angle, right? So now my force, if I want to know how much of this force is helping me along my path, notice that I have some triangles here. Maybe these triangles aren't very clear, but my force is going this way, and I want to know how much of that force is helping me in the direction of my path. What I'm asking is, if I were to project this force arrow down onto my path, what is the length of this force arrow? And the length of that force arrow is going to exactly be given by a dot product. And that's where my geometric interpretation is going to end, and we're going to go into our algebraic interpretation. So my vector line integral, our generic way of writing that is to say that my path is given by c, and my vector field is given by f, and I'm dotting it with ds. Notice that I'm parameterizing this by distance rather than time. And we're going to have to switch that because our c parameterization, we want to be able to compute it in terms of time. So what is this? Remember from our geometry, now I'm going to draw a curvy path. Let's say I have a curvy path, and this is my curvy path c of t, and I have some vector field. This is just going to be one representation of one vector at one point. Maybe I should draw an additional error there. This is my f of c of t. It's the, based at this point, c of t, the vector that's being given by my vector field. I want to know how much of this vector is along the same lines as my tangent vector. This is my tangent vector. So recall, our tangent vectors are the ones that are exactly perpendicular to our curve, because we want to know what component of our force vector is along the same direction as our tangent vector. Algebraically, what is our tangent vector? Our unit tangent vector, t, unit tangent vector was given by, it's the derivative, and I'm going to make it 1 unit in length, c prime of t. And if I want to know how much of this force vector is in the same direction as my unit tangent vector, because it's already a unit tangent vector, recall that it's exactly going to be my f dotted with t. F dotted with t ds. Great, we're part of the way there. That means that substituting in the fact that my t vector, my unit tangent vector, is exactly c prime divided by the magnitude of c prime of t, that gives me f dotted with c prime of t divided by the magnitude of c prime of t ds. And our final step is to notice the fact that we don't want to parameterize this curve with respect to distance. We want to be able to parameterize it with respect to time. And that gives us our almost final formula. If I want to convert my distance into time, we know that distance times velocity is equal to time. This is sort of a, it's a little heuristically derived, but I think that intuitively it gives a really good picture of what we're looking at. So this is telling us how much force is in the direction of the tangent vector. Force in direction of tangent vector. And then instead of ds, I want to have dt there, and so I'm going to have to multiply it by the speed. Speed times time equals distance. That's why ds is equal to this times dt. These two things cancel. And now you can write down the final formula that's going to go into your notes. So our vector line integral, we can have these two speeds cancel. Really, it's just going to be our vector field evaluated along our path, c of t, dot product with c prime of t dt, as t goes from whatever t's starting point is to t's ending point.